Let's get started. Today we'll be talking about hidden Markov models. Hidden Markov models are designed with the intention of modeling sequences. So one particular problem that deals with sequence modeling is sequence prediction. So this is a supervised version of this particular learning problem for modeling sequences. So this is a special case, arguably the motivating special case that started a lot of this research in machine learning, and it's part of speech tagging. So if X is a sequence of words, in this case, the first example, fish sleep, then Y would be a sequence of part of speech tags, in this case, noun, verb. In the second example, the dog ate my homework, Y would be the sequence determinate noun, verb, determinate noun, and so on and so forth. So this is part of speech tagging, which is a special case of sequence prediction, which is a special case of sequence modeling in general. Okay? And this is supervised learning because we have a Y that's been annotated, that's given to us by some annotator. So this is a very, within the context of everything that we've seen so far, this is a very sort of unique form of prediction task, since it's not just predicting a single number or a single class, or even multi-class prediction where it's one of a fixed number of classes. Here the number of predictions vary with the length of the input sequence. So what are some challenges? Well, as I just mentioned, it's a multivariable output problem. Then we have to make multiple predictions simultaneously. Furthermore, it's variable length, right? The input sequence length is not fixed. Oftentimes one assumes that there's an upper bound on the variable length, but in general, this is something that we have to be a little bit careful about taking into consideration of. Okay, so what if we just tried treating this problem like the way we've been treating most supervised learning problems in this class, right? Just multi-class prediction, right? So there are, in this simple example, there are 6 part of speech tags. And so, we'll have, a number of weights for each class, with the weights in bias terms if this is a linear model, right? We score all the classes, right, if they're capital K classes. And then we predict the class with the largest score, right? We've seen all of this before, right? If one were to take this very unstructured view of sequence prediction, can anyone tell me how many number of classes there might be? Yeah. Exponential the length of the sequence, right? So if we only consider length m sequences, right? In the unstructured multi-class prediction viewpoint, each possible sequence of y's is a unique class, right? So these are all possible length 2 sequences, right? And so we'd have to learn a separate parameter vector and bias for each of these classes, score all of them, and then predict the one that has the highest score for this input. This is what you would do if you were to apply what we talked about in the first 6 weeks of class in a very naive, unstructured way to this problem, right? So the number of classes is capital M raised to the M, or capital L raised to capital M, or capital L is the number of different part of speech tags, in this case 6, and capital M is the length, in this case 2, right? Those 36 classes, and this scales exponentially with the length of the sequence. So this is not attractive. Okay. Here's just another example for length 3, right? It gets a little ridiculous. If you treat every combination as a completely separate class with no relationship to each other, then you have to learn a separate weight vector per class. And here a class is a unique sequence, right? Of combinations, right? And this is exponentially large. This is not only exponentially large in the computational time, it's exponentially large in the storage, right? It requires exponential space to store this model. Okay, let's go to the complete opposite extreme, all right? Let's treat every word as an independent sample, right? So forget the fact that it's a part of a sentence. Let's just treat every word as a completely independent sample, right? So now we're going to predict make an independent multi-class prediction per word, right? So predict for I independently, predict for fish independently, and predict for often independently, right? And then we concatenate the predictions, okay? This is another way to go about this. So the number of classes equals the number of part-of-speech tags, so 6, right? Now we can just solve this problem by pretending everything's an independent prediction and ignore the fact that there's a sequential relationship between these inputs. Okay, so here's just one very simple model, right? Where we're modeling P of y given x, where x equals to each of these independent words, right? And so then we just make a prediction that has a maximal probability. And here, for simplicity, I'm going to consider nouns and pronouns to be the same thing. Obviously, we can make a more expressive output space definition, but for simplicity, noun and pronouns are the same thing in this example. And so the prediction that you would make with this model is noun, noun, adverb, right? And the correct prediction is noun, verb, adverb, right? So we made a mistake on fish, right? And the reason why we made this mistake is because in a vacuum, let's say for this training set, right? If you see the word fish, 75% of the time it's a noun, and only 25% of the time it's a verb, right? And so in a vacuum, in the absence of considering any other information, the best that we can do is predict fish, but it's wrong here. Because we're ignoring the fact that it's part of the sequence of words. Any questions on that? Okay. Right. So this is just sort of repeating what I just said. Independent predictions ignore word pairs. And pairs is sort of the simplest thing that you can think of. You could also consider triplets and so on and so forth. Right? Conditioned on the fact that the word fish is followed by a noun or a pronoun, fish is more likely to be a verb. We all know this. The model should know this. Right? This is what's known as a first order dependence, where we are looking at all adjacent pairs of words, right? In order to make a better prediction. And notice here that this particular reasoning here is not on the identity of the previous word, not on the identity of I, but on the prediction of the previous word. Right? This particular reasoning doesn't care what exactly is the previous word, just what is the prediction for the previous word. You might have a vocabulary of 1,000,000 words, but if you only have 6 predictions, this is a much more compact way of reasoning about what's going on. And I'll make this more formal. Basically, the entire lecture will be focused on this. So this is known as a first order dependence, also known as a first order Markovian dependence. You know, you can go higher order. Second order considers all consecutive triplets. Third order considers all consecutive 4 tuples, and so on and so forth. If you consider arbitrary order, right, then you get back to exponential size, right? Because all possible pairs, right, is somehow quadratic in some dimension, right? All possible triplets, second order, all possible triplets, somehow cubic, within some dimensionality. And once you get to arbitrary order, you're back to exponential. So this is the definition of a first order hidden Markov model. This is a probabilistic model. So even though I motivated in the context of part-of-speech tagging, this is a generative model that models the joint distribution of x comma y. And of course, once we train this, we can use standard Bayes rule to infer P of y given x. And so a first order hidden Markov model is fully specified by these 4 probability tables. So the first probability table is P of x given y. So if we're in state y, and here you can think of each state as a part of speech tag, right? So if we're in state y, what is the probability that the state y would generate the word x, right? We have a probability of transitioning from one state to the next state. If we're currently in state y sub I, what is the probability of the next state, y super I plus 1? And then we have some boundary conditions like the distribution of the start states, and whether or not we terminate. we took a look at graphical model representations in the past. And so this is the graphical model representation of a first order hidden Markov model. And from this graphical model representation, we can infer all sorts of conditional independence assumptions, right? So condition on observing y of 2, then the probability of distribution over x of 2 is completely independent of everything else, right? And that's specified here as a multiplicative factorization. Right? Furthermore, the transition probability of y also is factorized like this. Yeah? And so this is what this joint distribution is what specifies a hidden Markov model, a first order hidden Markov model. And I'll just let you stare at this for a few seconds while you, yes?
So is probability of n, is that the probability that that's the last element in the sequence? Or what is
Yeah, probability that the sentence is, the sequence ends.
Okay.
Yeah, so if you were to, sometimes people don't use it if you know you're going to predict a certain length, right? But some. So you make a special dictionary item, which is a start token and a stop token, and n would correspond to going to the stop token.
Are you assuming that you know y0?
Y0 is the special start state, yeah. It's unique.
Okay.
Yeah. You always start at Y0. Different people write it different ways. People write out the probability of, I wrote it this way for mathematical convenience. Some people have a distribution over the first y. So y sub 1, what is the distribution of it? I wrote it in this way, which says there's a unique y0. It's an abstract concept. And what is the probability of transitioning from y0 to y1? It's mathematically equivalent to saying what is the distribution over the start states, over the first word. Excuse me, the state that generated the first word. Yes?
For that ending probability, are there models that, if that's just saying like what the token ym is, that's not encoding any information about how big m is? Like if you see a noun, but it's the second token in a phrase versus the
So this is most useful, this end thing is most useful when you think about generating a new sentence. Right, so if we generate a new sentence, and I'll go over this in detail towards somewhere in the middle of the lecture. We would, again, flip random bits or in topological order, right? And at some point we have to figure out when we're going to end the sentence, right? If we don't have a prescribed length of the sentence, we just let it generate until it decides to stop. Then for every y sub I, it has some probability of going to the end.
What I'm asking is, I take that that's only modeling based off like what the token ym is, versus like let's say it's a noun, right? I imagine like a noun that's like at the 10th element of a sentence is more likely to lead to the end state than the second.
So
element.
that is not modeled here.
Yes. Is there a model that does incorporate that?
So time variant hidden Markov. So this is a time invariant hidden Markov model, where these probability tables are invariant to time, or where you are in the sequence. Time variant hidden Markov models do exist. They're more complicated. So this is basically the joint distribution of the hidden Markov model, right? So x and y are both sequences. X is sequence over words. Y is sequence over states. You can think of each state as corresponding to a part of speech tag in our example. And so this specifies the joint distribution, right? Okay, so now, suppose we want to model, like in every probabilistic generative model, we want to make queries on this model. That's what people often call these types of inferences, right? Inferences or queries on this model. For example, condition on a y. So suppose we fix a y. Let's model a probability distribution over sequences of x, right? And in that case, you could just literally just read off certain subsets of the probability tables that we've specified, and it is literally just this. Because every x, every token x is conditionally dependent of everything else, conditioned on its corresponding y. And therefore, this is the probability. That's pretty easy. Just repeating what I just said. Okay. So let's talk about the complexity of this model class, like how many parameters it has. Okay. So the bulk of the complexity comes from the first two bullet points. These two are basically just boundary conditions. The bulk of the complexity comes from these two. Right? So the first one, let's see, did I write this in? Yeah, okay, I wrote this in inverted order. So the modeling all state-state pairs, that's the second line, right? So this probability table, the size of this probability table is equal to the number of part-of-speech tags squared, right? And then the first one is the number is state observation pair. So condition of being in the state, what's the probability of observing this word, right? In the corresponding token in the sequence. And that is, the complexity of that is equal to the number of words times the number of tags, right? This is the same complexity as independent multiclass prediction, right? In independent multiclass prediction, we'd have to store a weight vector for every tag, right? And that weight vector is, the length of the weight vector is linear in the number of words if we use a bag of words representation. And so this is sort of the same complexity, we just have this additional complexity, right? And so if the number of words, right, if the number of distinct words is much larger than the number of distinct tags, then this isn't the storage complexity, the number of parameters of this model is not that much more than the number of parameters in independent multiclass, right? It's just number of tags and number of words plus number of tags squared. And the number of tags is 6, and the number of tags is 1,000,000 or whatever, 1,000, 10,000. Then this isn't that much worse than just the model complexity of independent multiclass. So a far cry from exponential. Of course, we're making some very strong independence assumptions in order to get the number of model parameters to this low with all these factorizations of the probability space. But the benefit is you get something that is able to consider adjacent pairs of predictions without spending an exorbitant amount of parameters to do so. Any questions on that? Yes?
How would you modify this algorithm if you want to handle a language like Chinese where the number of characters in a word may be uncertain?
Yes, how do you model Chinese where the character word boundaries are variable? So this actually also happens in English as well, by the way. For example, Professor Yisong is one entity actually, right? Sorry to be so self-serving. Usually people say like President so-and-so, but yeah, so that's a really good question. People handle it in a few different ways. Probably the most common way is to tokenize, is to run a tokenizer. So you parse the sentences into tokens, and then you run a hidden Markov model over the tokens. So now your dictionary is a Chinese word that's 3 characters long is a unique token. This increases the number of tokens in your dictionary by a lot, but that's what people do. And you saw this in the word-to-vec example, right? Some of the word-to-vec examples, some of the concepts were multiple words. Okay, so some of you might have already seen this, but there's actually a very close relationship between hidden Markov models and naive Bayes. Okay? So in the special case where the naive Bayes, below I'm drawing naive Bayes, where I just model every word or every token in the sequence independently, and above is the hidden Markov model, right? And in the special case where the naive Bayes model is only outputting 1x, so in the class on Tuesday, we consider the case where the naive Bayes is outputting multiple x's independently, right? But in the special case where it's only outputting one x, then naive Bayes is a special case of hidden Markov models where we don't consider transitions between the y's. We can also extend, of course, hidden Markov models where we're outputting not just a single x, but multiple x's per token in the sequence. That doesn't have a natural analogy to sentence modeling, but there are other domains where that actually makes sense. Okay, so let's go through just a really quick example. Suppose we had 2 words in our language, fish, sleep, and 2 tags in our language, noun and verb. Very simple example. And here's our conditional probability table of p of y, x given y. So we're just going to look at this particular table, right? So what is the probability that noun verb, right, generated fish sleep? You just multiply these 2 numbers together. So noun, let's see, noun generated fish, so noun generated 0.8 times 0.5, right? So that you could just compute these numbers. And you can compute this for any sequence of these sequences of these 2 words, for any sequences of these 2 part-of-speech tags. Yes.
Is the bottom one correct?
So noun go to sleep is 0.2, verb go to sleep is 0.5.
No, the bottom.
This one, right?
Yeah, now.
So the probability of noun generating sleep is 0.2, and the probability of noun generating sleep is 0.2. Oh, okay, I'll fix that. You're right. That's a typo. Yeah, I'll fix that. Never trust a professor to do math. Haven't done it in a while. Okay, so we can also do sampling. So hidden Markov models are generative models. So you can actually, once you have a fully specified hidden Markov model, you can sample sequences from it, right? Because you can just sample from this joint distribution, right? And so let's just first consider this conditional distribution, p of x given y. So we have a sequence of y, and we want to generate a sequence of x, right? Well, in this particular case, every x is conditionally independent because we're conditioning all the y's. And therefore, sampling a sequence of x conditioned on a y just boils down to sampling every x completely independent, right? Just like in naive Bayes. Okay, so that's pretty simple. But suppose we didn't know the y, right? We want to generate the whole thing, right? How do we do that? And so we're going to do forward sampling. Just basically what this basically means is we're going to specify the sequence and sampling in topological order. It's a little bit complicated because sequence is potentially variable length. Right here we're going to look at the case where it's variable length, right? And so the length is not a priori defined, so we just keep doing sampling until we sample the end state, and then we're done, right? And so you could rewrite this whole model. If we do a sampling procedure, if we're doing forward sampling as this sort of probability transition diagram, right? Notice that when we're doing sampling, right? Whatever x is, sampling the next y does not depend on any of the x's that we sampled previously, right? So this is the state transition diagram, probabilistic state transition diagram for the y's. And in whichever y we're in, either noun or verb, we sample one of the words from doing lookup table here, right? When we keep doing this until we jump to n. and then we're done. We've sampled the sentence. So we initialize at the start state. So the start state is unique. Then we sample a y sub I from this transition, so that you could just look it up from this diagram. If y sub I equals n, we're done, right? Otherwise, we sample x from this probability table, and then we'll go back to step 1. And we repeat it until we sample the end state. And that's how we sample a sequence from this model. And the sample here is just like in hidden Markov models. We pick a uniform random number, independent random number that's sampled uniformly between 0 and 1, and then we just sort of divide up that probability space to the proportions of the probabilities. Pretty straightforward there. Okay, here's another one where we're just going to ignore the fact that we have this n, and we're going to fix the length of the sequence. I think that should be capital M. Yeah. And we do the same thing. For the final mini project of this class, you will have to do this. I believe it's going to be for Shakespearean sonnets. So you train a hidden Markov model or some sort of sequence model, generative sequence model, on all of Shakespeare's sonnets, and you have to generate your own. So this is something you'll have to do. So a first order hidden Markov model is sometimes referred to as a memoryless model, right? And what that means is, suppose that we've sampled up to time step k, right? And we want to model the probability distribution of the remaining parts of the sequence, right? Well, actually, it depends only on y of k. It doesn't depend on anything else. So no matter what we've sampled in the past, it's sufficient to know what y of k is to model the probability distribution of the future. And in that sense, this is a memoryless model. Okay, now I'm going to talk about the Viterbi algorithm. How many of you have seen dynamic programming before? Okay, so about half the class. The other half of the class, there's going to be a recitation on dynamic programming next Tuesday. The Viterbi algorithm is an instance of dynamic programming. So this is the most common prediction problem in sequence modeling. This is the sequence prediction problem. This is what was the originally motivating part of speech tagging problem. Given a model, we want to and given an input x, we want to predict the y that has maximal probability given this x. The naive approach is to try all possible y's and choose the one with the highest probability. Right? That will solve this optimization problem. This is exponential in the length of the sequence, right? So we don't want to do this. So let's do something a little bit smarter. First, let's invoke Bayes' rule, right? So under Bayes' rule, we can write out the first term as this, and then we drop the, because we're solving over an argmax, we can drop the denominator because it's constant with respect to y. And then we can factorize using the law of conditional probability, p of y comma x or x comma y in the following form. And both of these are things that we can write out in this form. Okay, So this is just a repeat of what I wrote in the previous slide, where we want to solve this probability, we want to solve this argmax, and it factorizes into the following forms, right? And these are some definitions from before. So I'm going to I'm going to separate out solving for the last y in this sequence and the rest, right? So the first n-1 versus the rest. So this is simply rewriting the argmax as separating it out. So this is the equivalent problem. I just separated out the variables. Otherwise, they're equivalent. So I've done nothing here, other than a slight change in notation. And it's funny how much these types of derivations are all about just like manipulating notation until something becomes obvious, right? It's like 90% of the work in these types of derivations is manipulating notation. Now I separate out anything that involves the last y of m from the product, right? So this guy, is this product everything that does not involve y of m, and the two things that involve y of m, I factorized out. Okay. So at this point, we're going to exploit the memoryless property of hidden Markov models, right? The choice of y of m depends on the first n-1 y's only via this probability table. This is the only place where our choice of y of m depends on the previous y's, right? No matter what we did for the first n-2 y's is irrelevant, is not directly relevant, I should say, to our choice of y of m. And this is a property that's exploited in dynamic programming sort of all over the place. This is not unique to hidden Markov models. Is that a question? No. Okay. So I'm going to write it out. So this notation is admittedly a little ugly, but it was somehow the most sort of complete notation I could come up with. By the way, all of this is in a more rigorous form in a course notes that's on the website. So on the website, next to the lecture slides for this lecture, are course notes, sort of a textbook style course notes for hidden Markov models. You'll probably find those very useful for the homework. Okay, so we're going to call capital Y hat sub of k of v the best choice of the first k minus 1, y's, right? Where that ends in v. So it's the best length k. I should rephrase this better. It's the best length k sequence of y's that end in v, right? Which is for a specific part of speech tag, right? And I'm going to assume that the x's are fixed. So this is all over a fixed x, right? So I'm suppressing any dependency on x in this notation here. And y hat of k of n of noun, which is another state or another part of speech tag, is the best length k sequence, right? That ends in n, that ends in noun. Dynamic programming works by iteratively building up these two things as k increases. And in general, for more part of speech tags, the number of things you need to keep track of is linear in the number of part of speech tags. Here is just 2 right now. So the claim, the way dynamic programming works, and specifically for this instance of dynamic programming, the Viterbi algorithm. By the way, it's the same Viterbi that's the USC School of Engineering, Universal Conference School of Engineering. It's called the Viterbi School of Engineering. It's the same Viterbi. the claim is that there's an inductive property, which is that y hat of k plus 1 of, let's say, verb is equal to this plus verb, right? And this argmax is not over all possible sequences of k minus 1, or in this case k. It's only over all possible sequences of these two, right? So this y of 1 to k is either this guy or this guy. So we're going to check two things here. Not check something that's exponential in k, but just check simply 2. And then we pick the one that maximizes this quantity. That's the claim. And this particular probability right here, we'll recall that it factorizes in the following form. And this part is pre-computed, right? So in the process of computing this guy, computing this argmax, you can, through a very light bookkeeping, you can also compute this as well. Right. And this is a recursive definition, right? So, if you start with k equals, 1 or 2, you compute these solutions. In the process of computing these solutions, you compute the probabilities. You iteratively, recursively go to the next k equals 3, let's say. You want to compute this guy. You look through the previous two solutions you computed before, and then you just tack on. You can compute this probability by taking this pre-computed part and tacking on these two, and then choosing the argmax, committing to it, tacking on v, compute these two solutions for verb and for noun, for k plus 1, then you just iterate until you get to the end of the sequence. And in doing so, we've computed the best length k prefix ending in each tag for every tag, and for all such tags, and for all such k, for all such length k, from 1 to the length of the sequence. So let's sort of see this in a different way, right? So some people like to see it in a little bit more graphical way, so I'm going to just say the same thing again, using a little bit more of a pictorial perspective, okay? So here we're going to have 3 part-of-speech tags, noun, verb, and determiner, right? And in the base case, so the way you sort of reason about this is just like in inductive proofs. There's a base step, base case, and there's an inductive step, right? So in the base case, we're at the first token in the sequence, and it's just simply, computing the best length 1 sequence that ends in some token z, where z is a variable that denotes one of the 3 part-of-speech tags, is simply just, you could brute force that because there's only 3 choices, right? So we're going to store the best length 1 prefix that ends in verb, determiner, noun. That's simply the verb, determiner, noun, the 3 singleton sequences. And we're going to store the probabilities, right? These you can just look up from the probability tables. So the base case is pretty trivial. Okay, now let's talk about the inductive case. Now we're at k equals 2. Let's talk about the inductive case, right? So for the best length 2 prefix that ends in verb, right? We look at the best length 1. We look at all the best possible length 1 prefixes, right, ending in verb, determiner, noun, at the ending in length 1, right? And then we consider how they transition, right, from that to the length 2 prefix that ends in verb, right? And we select an argmax over these 3. And the argmax is, the argmax of this quantity. This thing is stored before, and then we just multiply by these 2 quantities. And then we choose the one that has the maximal probability. and this is again made possible because of the fact that hidden Markov model is a memoryless model. Everything about the future is conditionally dependent given the current y sub k, or in this case y sub k minus 1. Right? And then we commit, right? So it turns out that this transition will maximize this probability. And then we do it for the next guy and the next guy, right? So for the best length 2 prefix that ends in determiner, we consider transitioning from this sequence to adding a determiner to the end, this sequence to adding appending a determiner to this sequence, appending a determiner to this sequence, computing the probability tables, right? And now we store, the best length 2 prefixes that end in each of the part-of-speech tags, and we store their probabilities, the joint probabilities up to length 2, right? And then we continue, right? So when we look at the best length 3 prefix ending in verb, we consider appending a verb to the best length 2 prefix ending in verb, determiner, noun. We compute this probability table. We compute this probability by looking at the probability table. This guy is stored from before, right? And then we choose an argmax, and so on and so forth, right? And is that a question?
Yes. So that first mapping that you had, it doesn't necessarily have to be that there's a unique input for each of those outputs. The way that it is currently right now.
I mean, in practice, the probability that there's a tie is very, very low.
Okay. But so like from transition into verb, okay, could it be that say y1 of noun?
Keep in mind this is conditioned on a sequence of words.
Okay.
Right? And so the chances, I mean, yes, in principle, ties are possible. And so it's not unique.
But noun could be the most likely word transitioning into both verb and noun in y2, right?
Oh, yes, that's right.
Okay.
Yes. So the winner of this guy, for this guy, could also do this, in principle, yes. That's right. It's not a matching.
Okay.
So this is a fairly efficient algorithm. It's not exponential in the length of the sequence. The way you reason on whether or not this is correct, right? Whether this would give you the same answer as if you brute force the whole thing, right? And spent exponential time. It sort of sits on the claim that you only need to check, the best solutions from the previous step in this inductive reasoning, right? And so, let's see. So here, oh yeah, by the way, I should also mention, in this particular pictorial diagram, you could actually read off the solution, right? The best length 3 prefix that ends in verb is noun, verb, verb in this example. Or it's either noun, verb, 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 determiner, verb, or determiner, noun, verb. It's one of those 3, right? You can just read it off by the choices of the solutions from before. So it's one of those 3. So what is not possible, so you've eliminated the majority of possible solutions. You've eliminated verb, verb, verb as a possibility. You've eliminated verb, noun, verb as a possibility. Anything that's not consistent with one of these red arrow paths, you've already eliminated as a possibility. So suppose that the best possible answer, if you brute force this thing for length 3, is verb, 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 which we've already eliminated, right, as a possibility, right? Then we simply just prove that the solution to the recursive algorithm has higher probability. Therefore, we establish a contradiction, right? Therefore proving consistency, right? And the proof depends on the first order property. So it's actually a very short proof. This is not the full proof is a little bit more rigorous than this. This is just a sketch. But the probability of this sequence and this sequence differ in only 3 terms, right? this guy, this guy, and this guy, and none of them depend on the choice of the last term. What does that mean? That means by the inductive hypothesis, all of these were the best possible length 2 sequences, right? That's the inductive hypothesis, and so therefore there's no way that this is better. Because we already proved inductively that one of these was the best, and therefore you can't. This is not possible. The full proof isn't actually that much longer than just writing this out more formally. It's less than a page. And that's the whole procedure. You just recurse this until the end and you're done. Now you have to implement it. Actually, I'm serious. No one laughed at that. Okay. Okay, so that was the Viterbi algorithm. If that went a little fast for you, that's okay. We're going to do another lecture on Tuesday and a recitation of dynamic programming in general on Tuesday evening. Right. So for every k, from 1 to the length of the sequence, we iteratively solve for the best length k prefix, ending in each part of speech tag. But this iterative solving only depends on the previous solution, and therefore it's quite efficient, right? And then at the end, when we're done with this whole process, we just simply look at the best length m prefix ending in each part of speech tag, and by length m prefix is just the entire sequence. And we just picked one of those 3. In this case, there's 3 part of speech tags. We just picked the one of those 3 that has the highest probability, and that is the correct answer. Okay, so here's a numerical example. So this is the state transition. This is the probabilistic state transition diagram. You could create state transition probability tables out of this. And this is the observation probability table of observing a word given a current state or a part of speech tag that we're in. And so the first word is fish, right? We start from the start state. We look up this probability table. We solve for the best length 1 prefix that ends in each of the part of speech tags. It's the base case, right? It's simple. And here we're just going to go through one step of the inductive step, right? Which is, the second word is sleep, right? And so if fish were a verb, we consider the best possible transition from verb to, one of these 2. If fish were a noun, we consider the best possible transition to the next token, and for each of these part of speech tags. Those are the 2 options, and then we choose the best one. So here in this particular example, we actually reverse the for loop, the order of the for loop, right? If you were to implement this in practice, you could either write an outer loop on each of these and the inner loop for loop on each of these, or you could write the outer for loop on each of these and the inner for loop on each of these. Right? Doesn't really matter. Well, it might matter for computation reasons, depending on how convenient it is to vectorize the computation. But in principle, it doesn't matter. And these back pointers, you can read off these back pointers to get the best length k prefix. And here there's looking at a special n token as well. And then the highest probability one is fish sleep. So noun verb. Noun verb for fish sleep. in this example. Yeah, that's a good question. Can anyone tell me what might go wrong for long sequences in these examples that I just showed? Yes?
You just loop over the same set of words, essentially.
So the fact that we only do pairwise dependencies means that for very long sentences or sequences, just looking at adjacent pairs might not give you enough information. This is an issue. There's another issue as well that's more numerical in nature.
Then it would be extremely small.
I'm sorry?
Then it would be extremely small.
That's right. So these probabilities decay geometrically with the length of the sequence. Right? So you're going to underflow very quickly. Right. So in principle, everything here works out, checks out. But numerically, what I just described won't work as is. Okay? There's a very simple fix. Does anyone see it? Yes?
Logs.
Take the log. Correct. So rather than doing this product of the probabilities, we do a sum of their logs. So instead of storing the probability tables, we store the log of the probability tables, and we sum instead of multiply, and then everything works as is. Yeah, you have to do it this way on the homework. If you don't do it this way, it's just not going to work. Okay, so just to recap, we talked about sequence modeling, why independent classification doesn't work because it doesn't look at local context, right? We looked at Viterbi, right? Where we're training pairwise transitions, we're trying to model pairwise transition states in the standard Markov models. We have to run a dynamic programming to actually make these predictions. Any questions on that before I get into training HMMs? Okay. So we're going to start easy. We're going to start with supervised learning. So in the case where you get X and Y, right? How do you train, right? So this is we're going to train using maximum likelihood, just like we've always done for these probabilistic models. Again, we're going to look at some matrix. We're going to look at some matrix notations. Things tend to, once you get comfortable thinking about these in terms of matrix notations, things tend to get a lot cleaner in the code, a lot cleaner the way you reason about it. You get to exploit vector arithmetic in the processors, etc. So we're going to have two matrices. We have a transition matrix, which I'll call A. A is one of the most common ways. So if you look at the hidden Markov model literature, people use different notation, but this is one of the ones that's most, one of the dominant notations that people use in the literature. You use A to denote the transition matrix, you use O to denote the observation matrix. And this is, I didn't do anything special, I just rewrote everything, replaced by their matrix notation. Okay, so maximum likelihood, we're going to map, we want to, given a training set, capital S, we want to select the parameterizations of our hidden Markov model that maximize the probability of the training examples, right? Of generating the training examples, essentially, right? So for supervised learning, where we observe X and Y, you can just simply do counting, right? And I don't think I'll go through the derivation. It's the same rationale as naive Bayes, right? If you compute the gradient of these with respect to these parameters, set it at 0, the optimal solution is just counting, frequency counting. So in particular, for transitioning from state A to state B, so anywhere in any sequence, what is the probability of transitioning from state A to state B, so verb to noun or whatever. It's the number of times we observe in any sequence, at any location, in any sequence in the training set, an A to, is it A to B? This is B to A, excuse me, I wrote the rotation backwards. This is B to A, and then we normalize the number of times we see a B in the first one. Similarly, in the observation matrix, right, if we observe a word W given a part of speech tag Z, right, we just go over every sequence in our training set, go over every location in every sequence, and look at every place that has a part of speech tag Z, and then compute the fraction of those that is associated with the word W. And again, you could regularize this using pseudo counts if you want, but this is the basic idea. Same is the exact same idea as naive Bayes. That's it for supervised learning. Okay, let's talk about unsupervised learning. Right. So, sorry, we're going to talk about. I added a bunch of detail about why is it this easy. And it's easy because once you exploit these independence assumptions, everything decomposes into the same kind of problem that naive Bayes has, right? Naive Bayes, everything decomposes. If you condition on y, if each feature dimension is independent, because of all the independence assumptions, once you can condition on the y's, everything's independent. The number of parameters, again, is number of tags squared and words times and the observation matrix is number of words times number of tags. Right? And so this is a very efficient representation because you avoid directly modeling word-word pairings. Okay, so now let's talk about unsupervised training, right? In unsupervised training, we only have the sequence of words. We don't have their part of speech tags, right? But we still want to estimate, p of x comma y, where y is some low-dimensional, representation of the transition dynamics of the sequence of words, right? So, given a set of training examples, that this is the maximum likelihood, right? And again, you can write that out as marginalizing out over all possible y's. Right? This is just the law of one of the laws of total probability. So this is what we want to do. Okay. Okay, so why might you want to do this? I think we've talked about some of this in the context of unsupervised learning before. Here, I think the thing that I really want to emphasize is that you will actually use this to generate, your own sentences, your own sequences. Building these really rich generative models is a topic of very active research in the community right now. And some of the stuff that they've generated is just incredible. You'll generate your own. You may even trick some of your English literature major friends into thinking there's a new Shakespearean sonnet they've never heard of. That happened once in a previous version of this class. I kid you not. So the algorithm that we'll be using to do unsupervised learning for hidden Markov models is an instance of an EM algorithm. We talked about EM in the context of learning for clusterings. This is a different version of EM for learning hidden Markov models. In clustering, the EM was the unsupervised part was the cluster. What were the clusters? Here, the unmodeled part are the hidden states. right? The y's, right? So if we had the full parameters of the models, right, A and O, we can predict the y's for every x, right? So let's start by just initializing A and O arbitrarily, typically randomly, right? We predict the probability of the y's, right, at each training x. And then we use the y's to estimate a new A and O. This is at a high level, conceptually the same as when we were solving k-means, where we predict the memberships of every x to a cluster center, given the parameterizations of the model, which are the locations of the cluster centers. And then we estimate new cluster centers. Right? It's at a super high level, it's the same thing. Except now, instead of cluster centers, we have some latent space that generates the x, right, in a sequence. And then we just repeat this process until we've converged, just like in k-means. Okay, so let's talk about the E step. So given a parameterization, right, we want to predict, in this case, we want to predict the marginal probability of each y in the sequence, right? So what that means is we want to predict the probability that the ith token is a noun, determinant, or verb. So we want to compute this table. This is known as the marginal distribution of each y. So we're going to go back to the matrix formulation. So this is sort of the definition that we had. And then the maximization step is we're going to simply do counting again, right? So if we've inferred in the supervised case, the counting was very binary, right? It was each entry is either 0 or 1, right? In the unsupervised case, things are not binary. Things are softer. It's a number between 0 and 1, right? So we're going to look at these probabilities. So under the current model parameters that we had, we can predict the probability for every token in the sequence of transitioning from A to B, divided by the probability that that token is the y equals b at that token, rather than hard counting it as 1 or 0, right? But otherwise, it looks exactly like the supervised learning case. So the parameter estimation step, given these inferences, so we set an A and O, we make these inferences about our model, and then we use these inferences to train a new A and O in this form. So the training part is easy, it's just counting, or soft counting in this case. The hard part is actually computing these inferences. Let's see, I'm a little short on time. 15 minutes. So I'm going to go over this. I guess I might go over this a little quickly, but we have another lecture on Tuesday on hidden Markov models. So solving the E step. So it requires computing the marginals, right? And we're going to do this using dynamic programming. So here's the notation. We're going to have two vectors. We're going to call them alpha and beta, right? And alpha encodes the probability of everything, alpha sub z of I encodes the probability of everything up to the ith token, right? And with the ith token, with the y of I being z, where z is one of the states, condition, and here we assume that we have an estimate of the model parameters, right? And then beta looks at the reverse, right? Beta looks at the reverse of the probabilities, and it's only looking at the x's, condition on y of I equals to z. The reason why we compute these alpha and beta vectors, right? So at every location I, there's the number of alphas is equal to the length dimensionality of the hidden states. And of course, same with beta. So each of these you think of as vectors for every token in the sequence. The reason why we have these two definitions is because then we can use those two to quickly compute these types of quantities. Right? And then we're going to basically solve for these two sets of vectors using dynamic programming. We can also do something. We can also do something a little bit more complicated, right? Recall that some of the supervised learning tab, or some of the learning in the maximization step, where we have to estimate model parameters. Sometimes we need to compute this probability where it's a pair. We could also do that using the alpha beta vectors. It's a little bit more complicated, but you basically have to sort of fix. The alpha beta vectors don't meet exactly, like in this example, where they meet exactly. And they're one apart. And then you fix things in the middle using B and A. So let's talk about the Ford algorithm. So, by the way, I should mention that the algorithm for computing the alpha and betas is called the Ford backwards algorithm. It's a very famous algorithm. And the Ford refers to computing the alphas, and the backwards refers to computing the betas. So in the Ford algorithm, or sub-algorithm, we want to compute that set of alphas for every token in the sequence. Right? So, if this is the definition of alpha for alpha sub z, right, at the ith token, then you could write this out by summing over everything that is not explicit in this quantity, by marginally adds out the y's from from the first I minus 1 y's. Naively, this will take exponential time because the number of things to sum over is exponential in I, right? But we can compute this recursively just like the Viterbi algorithm, right? In the Viterbi algorithm, it was doing two things, right? It was computing the best possible sequence, and it was computing a probability of that best possible sequence, right? Here, we only care about that probability, right? And it's a probability over a sum, not over a max, right? In Viterbi here, it was a max here. Here it's a sum. So the base case is trivial, right? For the first token in the sequence, it's trivial. And then this is the definition of the recursive step, right? And again, it exploits the memoryless property of hidden Markov models in that it only depends. So for a sub z of I plus 1, you just sum over all possible alpha. For alpha sub z of I plus 1, you just sum over all the possibility for alpha of I, right? For each of the par speech tags, you multiply the appropriate transition probabilities and the observation probabilities of the word at the token I plus 1, and that's how you compute this guy. Right. So as I said before, Viterbi effectively replaces, in terms of the structure of the computation, effectively replaces the sum of the max, and it keeps track of both the value as well as what is the max, right? The identity of the max. Otherwise, it's you use the same type of reasoning to be able to do this type of recursive definition. The backwards algorithm is the same thing except backwards, and you can actually do this whole thing backwards, from the end of the token backwards in time. And this is the formula. Let's see. In the case where you have an ending, where different part of speech tags transition to the end token with different probabilities, you wouldn't put 1 here. You would put the something proportional to the transition probabilities. Yeah. Is that right? No. Sorry. I take back what I said. I was wrong. I take back what I said. I was wrong. This because this is over I plus 1. So, and this should be n. I'm sorry. I'll fix that in the slides right after class. This includes if you are considering a non-uniform transition to the end token. And so that's the forward backward algorithm, right? You run forward, you run backwards, and after you computed these two, then you can compute any of these marginal probabilities, right? You store these two vectors, sets of vectors. You compute any of these. Very, very efficient. So can anyone tell me the running time of Viterbi and the forward backwards algorithms? Can you tell me what the running time is? Yes?
Look, I forget what letter to use, but it looked to be, I guess, O of M, L, and...
You could just use the length of the sequence, the number of words.
Yeah, so you do it for each training word, and then for each of that, you have to do it for each I in the length,
so,
and then for each one you do the sum over the number of possible tokens, or like.
So it's linear the number of. It's a linear the length of the sequence.
Yeah, and parts of speech.
And linear in the part of speech tag.
And also the number of training examples.
Right. Okay. That's not quite right. It's actually if you think about this. Well, it depends on your perspective. But if I want to compute this for every possible z, then it sums over all possible part of speech tags. It's quadratic in the number of part of speech tags. So it's linear in the length of the sequence and quadratic in the number of part of speech tags, or the size of the hidden state. Yes.
So would that be like, I guess, ML plus L squared?
It's the number. It's m times L squared. Yeah. Okay, so that is a recap of unsupervised training, right? We're training only on the X, no Ys. We use the EM algorithm, right? So the Ys are considered hidden states. And this is actually why it's called a hidden Markov model, because in general the Ys are unobserved, right? And so we train using the EM algorithm, where we've initialized a random A&O matrix, all the parameters of our model. We infer these marginal probabilities, conditional having these marginal probabilities. We use the standard counting method, in this case self-counting, to infer a new set of parameters, and we repeat until we converge. Some questions like how do you choose number of hidden states? I'm surprised no one asked it. I guess everyone knows my answer. Cross-validation. And that is it. So just to recap, right? Hidden Markov models are used to do model sequences. One of the most popular tasks in sequence modeling is sequence prediction. And you want to have a model that avoids exponential complexity, but is also able to model dependencies between tokens in the sequence in a way that independent classification cannot address, right? Any questions on that? I'm sure there are a lot of questions. People are just sort of too dazed to ask them. And so for next week, the lecture next week is unstructured. I will not have prepared slides. We will go over whatever people are confused about. This is the homework 6 is the hardest homework in the class. So you can think of it as a glorified office hours. Recitation next Tuesday will be we'll focus on dynamic programming for those who haven't seen dynamic programming before. And yeah, I don't mean to scare people. Sorry if you guys are. It's really fun, guys. You'll feel really accomplished after this. So I'll see you guys next Tuesday.